Hi there, grade 10s. First time in a long time that I'm making a video specifically for grade 10s. So I would like to continue the discussion we had in class in terms of motion in one dimension. And I'd like to go to the topic of graphs. So we're going to use graphs to describe motion. And our first example is this graph. Sorry, I'm looking for my mouse. There you are. Okay, so we have this graph. The first thing to do is to find out what graph it is. And we can see here that it's a position time graph. Now, position, there are three types of motion. First is that the object can be stationary. Second is that the object could move at a uniform velocity or a constant velocity for that matter. And thirdly, the object could be accelerating uniformly. Now, I haven't even looked at the question, but if the zero refers to the point of reference from where motion is observed, then for the first 2 seconds in this object's motion, the object was stationary. I can see it there, that the distance that the object traveled from the point of reference was 0. Then the object had a parabolic graph from 2 to 4 seconds. So it means that every little second, the object goes much further. So at the point in time, 3 seconds, the object changed position from 0 to 1. And in the next second, from 3 to 4 seconds, the object went from 1 meter to 4 meters away from its reference point. So it means that this object accelerated from 2 to 4 seconds. Then from 4 seconds to 6 seconds, you have a linear graph. It means that for that period of time, the velocity was uniform. It traveled from 4th to 5th second. It traveled a distance of half a meter. So its velocity was half a meter per second. And in the next second, from the 5th to the 6th second, it traveled another half a meter to reach the position of 5 meters from the origin. I'd like to see what the question is. Oh, this is what they want to know. They want to see, they want us to describe the car's motion, which we have done. Words. In words, this car went for number A from 0 to 2 seconds. The car was stationary. Then from 2 to 4 seconds, there was a uniform acceleration. And from 4 to 6 seconds, the car was moving at a constant velocity, so uniform velocity. Question B asks us to draw a sketch graph of velocity against time for this motion. So for question B, a velocity time graph. Remember, we need to label the axis properly. These are sketch graphs, so you don't have to calibrate the axis properly. From 0 to 2 seconds, the velocity was 0 meters per second. From 2 seconds to 4 seconds, the velocity increased. I don't know by how much, but it increased. Because of the uniform acceleration, the velocity increased by the same amount per second, so the graph will be a straight line graph with a gradient. And from 4 seconds to 6 seconds, the object moved the same distance per second, so it means that the velocity was constant. So that part of the graph is parallel to the time axis. Question C wants us to draw a sketch graph of the acceleration against time. So we need to label the acceleration time graph. 2 seconds, 4 seconds, 6 seconds, and A for acceleration in meters per second squared. In the first 2 seconds, the object wasn't moving, so the acceleration is 0. And then next 2 seconds, I'm not sure, we don't know what the acceleration was, but it was definitely positive. And for that, the acceleration must be parallel. The line drawing acceleration, representing acceleration, must be parallel to the time axis, because we work with uniform acceleration only. And then when the car was going at constant velocity from 4 to 6 seconds, the acceleration was once again 0. So this is how we can move from one graph to another graph, sketch graph wise. You might be required to be more accurate, but this question didn't lend it to be more accurate. Let's go to the next example. Right, let's clear all these drawings. The next example gives us this graph, and it says that we need to describe the motion of the car in words. We need to determine the area under the velocity time graph and indicate what you have calculated. We need to determine the total distance covered by the car. We need to draw a sketch graph of position against time for the car's motion. And we need to draw a sketch graph of the acceleration versus time. To sort out all my other things here. Right. So to describe the motion of the car here, in the first 5 seconds, from 0 to 5 seconds, the car's velocity changed from 0 to 4. And because the graph, velocity time graph, is linear, we know, and it's got a gradient, and the gradient is going to be equal to the acceleration. So to answer question A, from 0 to 5 seconds, the car experienced uniform acceleration from 0 meters per second to 4 meters per second. Then from the 5-second mark to the 12-second mark, from the 5 to 12 seconds, the car moved at constant velocity of 4 meters per second. Then from 12 to 14 seconds, the car decelerated from 4 to 0 meters per second. And because that is a straight line, I know that it is uniform deceleration. From 4 meters per second to 0 meters per second, it stopped. And all this motion up to now was in one specific direction. At 14 seconds, the car started reversing. So from 14 to 15 seconds, the car reversed. Or it turned around and now it's going backwards. It's going in a negative direction of motion. So all this motion from 0 to 14 seconds was in one, and we can call it the positive direction. And the last second, the car was reversing, and we can call that the negative direction of motion. So the car reversed from 0 meters per second to 2 meters per second. And you can see that the value on the y-axis is a -2, meaning that the car is traveling in the opposite direction to its original motion. Right, this brings us to the end of question A. Let's clear all the drawings here. Question B says, determine the area under the velocity time graph and indicate what you have calculated. So if we calculate the area under the graph, this graph has a few areas. It's got the area under this triangle, it's got the area under this rectangle, and it's got the area under this triangle, and it's got this area here. Now to just draw a motion map to explain the situation is that this car moved from time 0 to time 5 seconds. This car was accelerating in one direction. Oh my. The car was accelerating in the forward direction. So he was accelerating. The A was not 0. Then he carried on moving forward at a constant velocity. So V was constant. Then he carried on a further 2 seconds, and for that period of time, he was decelerating. So the acceleration was not 0. Then he turned back and he started moving back more towards home again. So this was uniform acceleration backwards. So there A was not 0 again. Right. Let's tackle this question. So determine the area under the velocity time graph. The area under a velocity time graph will be velocity times time. So that will give us displacement. From the equation V equals delta x over delta t, if you multiply velocity by time, you will get displacement. Now, we could break it up into small parts. The first is a triangle, so it's half times 5 times 4, plus a rectangle, which is from 5 to 12 is 7 times 4, plus another triangle that would be a half times from 12 to 14 is 2 times 4, which is the perpendicular height, plus another second, 1 second times minus 2 is the perpendicular height. Because we're working with vector quantities, we need to include the direction. We need to accommodate the direction. So that first part would be 10 meters. This part is 10 meters. The area represents the displacement. This part represents 28 meters. This part represents 4 meters. And here we're going back 2 meters. To add all this, get to, what did I do? I multiplied. That can't be true. That's 10 and 28 is 38, and 4 is 42, and negative 2, which gives us 40 meters. And this will be the displacement. Okay, I already said that. Right, so that was question B's answer. Question C asks for the total distance. Now, distance is not a vector quantity, it's a scalar quantity. So a scalar quantity will not consider the backward motion as a negative direction. So for this, it will be the 10 meters traveled in the first 5 seconds, the 28 meters traveled in the next 7 seconds, the 4 meters traveled in the next 2 seconds, plus the 2 meters traveled while he was walking backwards. That is distance. So this adds up to 44 meters, the distance that the car covered. You are welcome to pause the video anytime you need to have some talking or some discussing time to clarify things. Right, let's clear it so that we can. So the total distance was 44 meters and the total displacement was 40 meters. Right, number D says draw a sketch graph of position against time for the car's motion. So the position time graph would be a sketch graph, x in meters. Now here, because we have the different values of time and displacement, we could fill it in. So for the time axis, in the first 5 seconds, this car traveled 10 meters and he was accelerating. So the graph must be parabolic for the first 5 seconds. Then the car went 28 meters further. That took it to 38 meters from 5 to 12 seconds. That the position time graph will be a straight line because the velocity stayed constant. Then for 2 seconds, the car went another 4 meters to 42 meters. And in that time, the car was decelerating. So for that short period of time, we have a negative parabola again, because he's going to go a shorter distance as he decelerates. Then the car in the next second turned back and went back 2 meters to a position of 40 meters. So this is what the position time graph would look like. First 5 seconds acceleration, so it's a smiley parabola. Next 7 seconds straight line. Next 2 seconds a crying parabola, but still going forward. And the last second he turns back and he would end up 40 meters from the origin. Right, numbers E wants us to draw a sketch graph of acceleration versus time. I'm going to squash it in here. So acceleration versus time graph. I think this graph has a negative acceleration part to it, so I better give it a negative part to the axis. So this is our acceleration in meters per second squared graph. The first 5 seconds, we haven't calculated the acceleration, but we could. It would be 4 divided by 5. So that would be what? 4 divided by 5. My fingers are doing the wrong thing here. So that's at 0.8. At 0.8 meters per second squared, the car would be accelerating in the first 5 seconds. Then next 7 seconds, the car would be moving at a constant velocity, so the acceleration is 0. The next, we can go from 12 to 15 seconds. The car has a negative acceleration. The gradient is negative here. So the gradient, this is one straight line. So the gradient would be -2 minus 4 divided by 3. So that would be -2. An acceleration of -2 meters per second squared from the 12-second mark to the 15-second mark. Right, let's move to the next example. Example 3 says that we're back to a position time graph now. Oops, sorry. And they say that we need to determine the velocity of the athlete during the first 4 seconds and then during the last 3 seconds. So it's a position time graph from the origin of motion. For 4 seconds, the car traveled 4 meters away from his origin, and because of this being a straight line, the car traveled the same distance every second. He traveled 1 meter in every second. We can say that it's uniform velocity. The velocity will be equal to the gradient. And you need to show how you calculated the gradient. You could use 4 and 0 divided by 4 and 0, which gives us 1 meter per second as the velocity. Then the velocity during the last 3 seconds, this person is standing still a distance of 4 meters from the starting point. So the velocity there from 4 to 7 seconds is 0 meters per second. The gradient of the graph is 0. That is why I know that the velocity is 0, because 4 minus 4 is 0, divided by 7 minus 4, which is 3. So we get a 0 meters per second as velocity. Righto. We can go to the next example. In this example, the acceleration versus time graph for a car starting from rest is given below. The first thing we need to do is describe the motion of the car. The second thing is we need to calculate the velocity of the car and hence draw a velocity time graph. So in the first 2 seconds, we've got uniform acceleration of 2 meters per second squared, and it would be in a specific direction. Then we've got uniform velocity, where the acceleration is 0. And then we have uniform acceleration in the opposite direction. Now, this could mean that the guy could be decelerating in the forward direction of motion, or he could have turned back. And he was reversing. One of those situations. Now, so I have described the motion of the car. The second part to the question says calculate the velocity of the car and hence draw the velocity time graph. Now, from a displacement, or sorry, from a position time, oh my, late at night. From an acceleration time graph, the velocity or the change in velocity would be the acceleration times the time. So the area under this graph. So 2 times 2 would be 4 meters per second. So in the first 2 seconds, the car moved from a 0 to a 4 meters per second. Here, I guess this car was moving at a uniform velocity of 4 meters per second. You see the area gives us the change in velocity. And here, the change in velocity from 4 to 6 seconds is minus 4 meters per second. That is the area under this graph. So if he went for, if his change in velocity is minus 4 and he was going at 4, he would be stopping at the time he got to the 6 seconds mark. That is if we consider the deceleration, which is the one that I'm opting for. So my velocity time graph would look like this if I consider his motion in one direction. So in the first 2 seconds, his velocity changed from 0 to 4. And then in the next 2 seconds, he was traveling at a constant velocity. And in the last 2 seconds of motion, he was moving forward, but he was going to a stop from 4 meters per second to a stop. Right. Where are we now? Sorry. Right, grade 10s, I'd like you to go to your textbook on page 275, and I'd like you to do number 4 and number 5. That is of exercise. Sorry, a bit slow. 18. Right. Thank you very much for watching. I hope it clarified some things to you.